For over a century, the automotive industry operated under a singular, unquestioned paradigm. It was a world of internal combustion engines, massive global supply chains, and incremental yearly updates. When a new company emerged from Silicon Valley promising to build electric vehicles, the old guard looked on with a mixture of amusement and pity. Tesla looked to the untrained eye like a car company. It had 4 wheels, a steering wheel, and a chassis. But to view Tesla merely as an automaker is to fundamentally misunderstand what was actually being built. Its deeper ambition was never just to swap a gas tank for a battery pack. The true objective was to rewrite the rules of manufacturing, software, energy distribution, and how the world thinks about the vehicle itself. To understand the magnitude of this disruption, we must first look at the state of the industry Tesla was attempting to enter. By the early 2000s, legacy automakers had perfected a highly specific, highly rigid business model. They were no longer true manufacturers in the classical sense. They had become system integrators. Brands like Ford, General Motors, and Volkswagen designed the exterior shell, engineered the internal combustion engine, and marketed the final product. But beneath the surface, the actual components of the car, the brakes, the seats, the electronic control units, the infotainment screens were outsourced to a massive, sprawling network of Tier 1 and Tier 2 suppliers. This system was a marvel of late 20th century globalization. It allowed legacy automakers to keep their capital expenditures relatively low, shift the risk of manufacturing to third parties, and focus on assembly and brand management. It was incredibly efficient for building gas-powered cars at scale, but it contained a fatal hidden flaw. Because every component was sourced from a different supplier, a traditional car was essentially a Frankenstein's monster of disparate parts, each running its own proprietary closed-loop software. The engine didn't talk to the brakes. The infotainment system didn't talk to the climate control. They were isolated black boxes. When Tesla was founded, it was universally dismissed. The early days of the company were defined by mockery, rapid cash burn, and a series of near-death moments. The original Tesla Roadster was built on a modified Lotus Elise chassis, and the company struggled to marry thousands of laptop batteries to a traditional automotive frame. In 2008, the company was days away from total bankruptcy. The financial press wrote their obituaries. Auto executives scoffed, viewing electric vehicles as glorified golf carts, niche toys for wealthy environmentalists that would never achieve mass-market viability. But while the public and the press were focused on production delays and Elon Musk's public struggles, they missed the architecture being quietly laid down beneath the surface. Musk and his team recognized that the traditional automotive supply chain was a trap. If Tesla relied on the existing network of legacy suppliers, they would inherit all the limitations of a legacy automakers. They would be forced to build a fragmented, slow-moving product. To break the old value chain, Tesla had to do something that had not been attempted since Henry Ford's River Rouge plant in the 1920s: radical vertical integration. Most people believe vertical integration is simply a cost-saving measure. In reality, it is an architectural prerequisite for absolute control. Tesla realized that to build a genuinely smart electric vehicle, hardware and software could no longer exist in separate silos. They had to be designed simultaneously by the same teams under the same roof. Instead of outsourcing electronic control units to dozens of different suppliers, Tesla engineered a centralized compute architecture. A legacy car might have 80 to 100 separate microprocessors scattered throughout the vehicle, each governing a single function. Tesla consolidated this into a handful of central computers entirely designed in-house. This invisible structural decision birthed the software-defined car. Because Tesla controlled the central nervous system of the vehicle, it could do something no other automaker had ever done: over-the-air updates. To the public, an over-the-air update meant waking up to a car with a new user interface or a fun new Easter egg on the screen. But strategically, this was a devastating weapon against the old world. In the traditional model, the car's value peaked the moment it was driven off the dealership lot. From that second forward, it was a depreciating asset with stagnant technology. If a legacy automaker wanted to improve the anti-lock braking system or optimize battery efficiency, the customer had to buy next year's model. Tesla inverted this reality. By decoupling the software from the physical hardware, limits a Tesla purchased in 2018 could receive a software patch in 2020 that physically reduced its braking distance, increased its acceleration, or entirely overhauled its autonomous driving capabilities. The car was no longer a static piece of hardware, it was a computing platform on wheels, continuously evolving. Legacy automakers could not replicate this even when they tried. They could not send a unified software update to a car because they did not own the software governing the individual components. Their outsourced supply chain, once their greatest asset for scale, had suddenly become an inescapable prison. But rewriting the software architecture of the vehicle was only the first layer of the strategy. To truly replace the internal combustion engine, Tesla had to solve a much darker, much heavier problem: the physical reality of manufacturing at a global scale. The technology industry is famously built on the economics of zero marginal cost. In the digital realm, software can be duplicated infinitely for nearly free. But cars are made of atoms. They require steel, aluminum, glass, and intense human labor. They are unforgiving, heavy, and governed by strict laws of physics and complex, slow-moving supply chains. For decades, automotive factories were viewed simply as assembly points, the final destination where outsourced parts converged to be bolted together. Tesla's leadership, however, viewed the factory differently. They conceptualized it as the machine that builds the machine. If you wanted to build cars faster, cheaper, and with tighter tolerances, you could not just iterate on the design of the car. You had to engineer the factory itself as if it were a highly complex integrated microchip. This philosophy materialized in the concept of the Gigafactory. When Tesla announced the first Gigafactory in Nevada in 2014, the scale seemed completely disconnected from reality, but the strategic map was cold and inescapable. To achieve mass market volumes, specifically to produce 500,000 vehicles a year, Tesla calculated that they would need more lithium-ion batteries than the entire global supply chain was currently producing combined. A legacy automaker would have looked at that constraint and concluded that high-volume electric vehicles were a mathematical impossibility. They would have waited for suppliers to scale up first. Tesla chose to internalize the bottleneck by building the largest battery plant in the world. They weren't just securing their own supply, they were preemptively starving future competitors of raw materials. They realized that in the electric age, the company that controls the battery cell controls the industry. But forcing this new manufacturing paradigm into existence nearly killed the company a second time. This era, famously known as the Model 3 production hell between 2017 and 2018, serves as the ultimate stress test of Tesla's underlying philosophy. To the public and the financial media, this period looked like a catastrophic failure of management. Tesla was missing production targets by massive margins. They were building cars in literal tents in the Fremont factory parking lot. The executive team was sleeping on the factory floor, visibly exhausted as Wall Street aggressively shorted the stock, betting heavily on imminent bankruptcy. The surface story was that Tesla simply didn't know how to build a car at scale. The deeper reality was that Tesla was attempting to build an alien dreadnought, a manufacturing system so heavily automated that the speed of production would be limited only by aerodynamic friction, not human movement. They tried to automate tasks that humans naturally do better, like threading flexible wires through complex, tight spaces. They pushed the boundaries of manufacturing physics too far, too fast, and their own system broke under the pressure. Yet the pain of production hell was not a sign of failure, it was a brutal crucible of learning. By pushing the system to its absolute breaking point, Tesla discovered exactly where the physical limits of modern automation lay. They ripped out the excessive robotics, reinserted human labor where it was most efficient, and finally broke through the bottleneck. When they emerged from this period, they had not just successfully manufactured the Model 3, they had forged a proprietary, highly efficient manufacturing blueprint that could be rapidly cloned. The proof of this hidden victory was seen a few years later, when Tesla built Giga Shanghai from an empty dirt lot to a mass-producing factory in less than 12 months, a speed previously thought impossible in the slow-moving automotive world. Alongside the reimagining of the factory was the reimagining of the infrastructure. A smart, high-performance electric vehicle is effectively useless if it cannot be driven long distances. In the early days, range anxiety was the single greatest psychological barrier to electric vehicle adoption. The traditional automotive mindset dictated that infrastructure was someone else's problem, Ford and General Motors did not build gas stations in the 20th century. They relied on the oil industry and independent franchises. Naturally, legacy automakers assumed they would rely on governments, municipalities, or third-party energy startups to build out electric charging networks. Tesla understood that when you are introducing a paradigm shift, you cannot rely on the old world to build your foundation. They realized that the charging network was not a secondary accessory. It was an integral, non-negotiable part of the product ecosystem. So, they spent billions building the proprietary Supercharger network. For years, critics called this a massive distraction and a waste of capital, but strategically it formed an impenetrable moat. While competing electric vehicles eventually entered the market, their owners were forced to rely on a fragmented, unreliable patchwork of third-party chargers with broken card readers, confusing interfaces, and slow charging speeds. Tesla owners, conversely, experienced a seamless, vertically integrated loop. The car's internal navigation system communicated directly with the charger, preconditioned the battery-on approach to maximize charging speed, and authorized payment automatically the moment the cable was plugged in. Tesla had essentially built a private global energy monopoly for its own customers. This vertical integration extended to the very final layer of the customer experience, sales and service. For a century, automakers relied on the franchise dealership model. But dealerships make the vast majority of their long-term profit from servicing internal combustion engines, oil changes, transmission repairs, spark plug replacements. Electric vehicles, possessing a fraction of the moving parts, require almost zero routine maintenance. A traditional dealership is therefore economically disincentivized to sell an electric vehicle. Recognizing this fatal misalignment of incentives, Tesla bypassed the dealership model entirely. They chose to own the customer relationship directly, from the digital point of sale on the smartphone to the physical delivery and the mobile service fleet. This wasn't merely a modern customer service initiative, it was a strict structural necessity. By selling directly, Tesla maintained absolute control over their pricing, eliminating the haggling, the arbitrary markups, and the predatory financing tactics that had defined the traditional car buying experience for nearly a century. More importantly, it allowed them to establish a direct, unfiltered data feedback loop with the end user. If a customer experienced a software glitch or a mechanical irregularity, the diagnostic data flowed straight to the engineering team in California in real time, not into a dusty filing cabinet at an independent franchise in Ohio. This closed loop was the final piece of infrastructure required to make rapid software-like iteration genuinely possible in the physical world. But the most profound element of Tesla's hidden system is something that is still largely misunderstood today: its data and artificial intelligence architecture. Most casual observers view Tesla's autopilot and full self-driving capabilities simply as a product feature, a high-tech convenience add-on designed to compete with advanced cruise control. In reality, it is a massive, decentralized data-gathering engine designed to solve one of the hardest problems in artificial intelligence: real-world visual navigation. Legacy automakers and well-funded tech competitors attempt to test their autonomous driving software using small, localized fleets of highly specialized, incredibly expensive sensor-laden vehicles, usually restricted to geo-fenced cities. Tesla, by contrast, leveraged its own consumer base. By equipping every single vehicle rolling off the assembly line with a standard unified suite of cameras and a proprietary neural net computer, Tesla transformed its customers into a massive unpaid fleet of global data collectors. Millions of Teslas are currently driving billions of miles across the globe, encountering every conceivable edge case, extreme weather condition, and bizarre human behavioral anomaly. This vast ocean of visual data is continuously fed back to Tesla's Dojo supercomputer, training their neural networks at a scale and speed that is mathematically impossible for any legacy automaker to replicate. When engineers from competing companies tear down a Tesla, they do not find standard automotive parts, they find military-grade compute architecture. Tesla is not simply trying to build a self-driving car. They are building the first generalized, real-world, physical, artificial intelligence engine, using the vehicle simply as the initial host body to map the physical world. As this software dominance grew quietly in the background, Tesla never stopped attacking the physical cost structure of the car itself. Just as they realized traditional supply chains were too slow, they eventually concluded that traditional metal stamping was entirely too complex. A conventional car chassis is constructed by stamping, welding, and gluing hundreds of individual pieces of sheet metal together. It requires massive factory floor space, hundreds of expensive robots, and introduces endless points of potential failure and misalignment. Tesla's solution was to look outside the automotive industry entirely, turning to the principles of the toy industry and heavy-duty aluminum die casting. They commissioned the creation of gigapresses, the largest high-pressure die casting machines ever built on Earth. Instead of painstakingly assembling a rear underbody from 70 different stamped parts, they injected molten aluminum into a massive building-sized mold and cast the entire structural piece as a single, solid object in milliseconds. This singular manufacturing innovation eradicated hundreds of robots from the assembly line, slashed production time, reduced the physical weight of the vehicle, and fundamentally lowered the cost floor of electric vehicle manufacturing. Today, the very legacy automakers who once laughed at Tesla's production capabilities are desperately trying to reverse engineer this gigacasting process to save their own deteriorating margins. Yet even if we fully grasp the software, the massive data network, and the manufacturing revolution, we still only see half the picture. The final, most expansive layer of Tesla's strategy transcends the automotive industry entirely. It lies in the profound meaning behind the name the company adopted when it quietly dropped the word motors from its corporate title. Tesla is, at its core, a distributed energy company. The lithium-ion batteries powering the cars are fundamentally identical to the batteries needed to stabilize the fragile global electrical grid. While the world watched the sales figures of the Model 3 and the Model Y, Tesla was quietly scaling its Megapack and Powerwall businesses. They deployed massive utility-scale battery installations to stabilize power grids everywhere from South Australia to Texas and California. They engineered Autobidder, an automated high-frequency energy trading software platform that allows these massive battery farms to autonomously buy electricity when it is cheap and abundant and sell it back to the grid at a premium when demand peaks. The master plan was never just to replace gas-powered cars on the highway. It was to build a vertically integrated, sustainable energy ecosystem, solar roofs to capture the energy, batteries to store it, sophisticated software to distribute it, and vehicles to consume it. The car, as it turns out, is simply the most visible mobile node in a much larger, decentralized power grid. This is exactly why the traditional automotive industry now finds itself trapped in an existential crisis. For over a century, they optimized their massive, sprawling operations to do one thing perfectly: manufacture internal combustion engines using a highly fragmented, globally outsourced supply chain. They spent billions perfecting a game that the market has suddenly decided is no longer being played. When legacy giants attempt to transition to electric vehicles, they are not just changing the powertrain of a car. They are fighting the immense inertia of their entire corporate structure. They are burdened by massive legacy union contracts built for the internal combustion era. They possess deeply fragmented software architectures that cannot be unified for over-the-air updates. They are chained to franchise dealership networks that actively resist the electric transition to protect their service revenue. And they face a profound, terrifying lack of control over the global battery supply chain. They are fundamentally trying to build software-defined machines using the physical, organizational, and philosophical architecture of the 20th century. Tesla survived its near-death experiences, defied the short sellers, and emerged as one of the most valuable companies on Earth, not because it built a slightly better luxury car. It won because it systematically dismantled and rebuilt every single constraint of the industry it chose to enter. From absolute vertical integration and centralized software to the unprecedented Gigafactory footprint, proprietary global charging networks, and direct-to-consumer sales, they engineered an entirely new paradigm that rendered the old rules obsolete. The ultimate strategic lesson hidden within this story is profound. When a legacy industry has spent a century hyper-optimizing for the past, the incumbent's greatest historical strength becomes their fatal, structural weakness. In these rare moments of deep technological transition, the ultimate victor is rarely the one who tries to play the old game slightly better. The winner is the one who completely refuses to accept the inherited constraints. The winner is the one who dares to build the infrastructure, the software, and the physical reality of an entirely new system from the ground up. Which company should we decode next? The one that joined an industry, or the one that tried to rewrite it?